This is a walkthrough of problem 9 on practice exam 3 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We have the energy usage per mile in a Tesla Model Y. So there's a minimum, and the faster you go, the energy usage goes up, and the slower you go, from about 40, the more energy that you use. So by measuring the slope of the line at 70 miles an hour, right here, estimate the change in the energy usage per mile, EPM, energy usage per mile, similar to gas mileage in an ICE car, internal combustion engine, with speed. So if I go a little bit over at 70, how much does my energy increase? Or if I slow down a little bit at 70, how much does my energy use decrease? That's part A, and we'll worry about part B later. So I want to get the energy, the change in the energy usage with speed at 70 miles an hour. So we're going to use a tangent line. We're going to mark the point at 70 miles an hour. There it is. And we're going to add a good tangent line. There it is. The rise is pretty easy. 200 miles an hour, 200 watt hours per mile to 400 watt hours per mile. So that's 200 watt hours per mile. That's the rise. The run looks like, I'm going to say 43 to 90, which is 47 miles an hour. And the slope is the rise over the run. So about 4.25 watt hours per mile each mile per hour. So in traveling close to 70 miles an hour, the power use increases by 4.25 watt hours per mile each mile per hour faster the car is traveling. Of course, the rate goes up as you go faster, but that's the rate around 70 miles an hour. Part B, take the derivative of both sides and then solve for d EPM per dV at 70 miles an hour. We have the normal equation. So the speeds increase from v to v plus dv. There's an infinitesimal response in the EPM, which we define as d EPM. And this is pretty ugly. We've got a bunch of constants in there. Let's just call them A, B, and C. So now the equation looks like that. Here's A, here's B, and here's C. So we can take the derivative. We'll throw the constants back in later. So there's our start. We change V. Everywhere we see a V, we put in a V plus dV. And then we have this change in energy use per mile. So we square out that V plus dV. That's right here. We drop the dV squared term as infinitesimal relative to dV. And then we can subtract the EPM. The normal equation for the EPM is AV squared minus BV plus C. So we get rid of that from both sides. The difference is this constant A times 2V dV minus this constant B times dV. We can put the constants back in, and that's what we get. Divide by dV to get the slope, and there we have it. This is the slope at any V right here. Plug in V, that's the slope. So at 70 miles an hour, we just plug it in right here. Get the slope. We punch the buttons on the calculator, and this one's 10.64 watt hours per mile an hour. Subtract 6.42, we get 4.22 watt hours per mile each mile per hour. And if you remember, we got 4.25 from the tangent line, and we're very happy with that. Close enough. The tangent line is tough. Part C asks, use the derivative to determine the speed at which the energy use is a minimum. So the equation for the slope at any speed is this. We have this. We want to find the point where the slope is 0. So we move over a little bit in speed, and the energy use doesn't change. That happens right here. So if we go over an infinitesimal amount, the energy use doesn't change. There's the tangent line. The tangent line's horizontal. I'm in a flat spot. So to find that point, we just set the slope equal to 0. Here's the slope, d EPM dV. Set that equal to 0. And now we can solve this for V. And that's just algebra. We just put V on the other side and divide by that. So we get 42 miles an hour, and we're not surprised. There it is right there. We knew that was roughly the minimum when we started.